Yet another session of Resilient Talk. And today's topic is landslide mitigation measures and strategies. As we all are aware, landslides, it is a geological phenomena with the potential to cause a widespread devastation, and it is one of the most prominent disasters as of concern for India. So as we expand societies into hilly and mountainous regions, the understanding of landslides becomes very, very crucial for a sustainable development and disaster preparedness. So landslides are primarily caused by, geological phenomena and various human activities. And today's topic and today's webinar on landslide mitigation is very, very important to see how this natural disaster can be actually mitigated from the various technologies available to us, and what are the required preparedness. So I hope today's Resilient Talk will deliberate on the resilience of the landslide mitigation measures and strategies, which is much needed for reducing the likelihood as on today. So today we have wonderful 4 speakers today who are experts on landslides. We have Dr. S. Krishnan, who is assistant professor at IIT Roorkee. Dr. Parvati GS, she's a principal scientist at Central Road Research Institute, New Delhi. Dr. Hemlata, assistant professor at Amrita Vishwa Vidyapeetham, Amritapuri. And Dr. Sansar Raj Meena, assistant professor at University of Padova, Italy. So before I hand over the floor one by one to all the speakers, I welcome you all once again. And I welcome all our participants as well. So our first speaker is Dr. S. Krishnan. Before I hand over the mic to him, I would just briefly like to introduce him. Dr. S. Krishnan is assistant professor at Center of Excellence in Disaster Management, Indian Institute of Technology, Roorkee. He holds a master's in geosciences from Bharati Dasan University, India, and a doctorate in engineering and field engineering for the environment from Hokkaido University, Japan. His research specializes in understanding the mechanisms of shallow landslides and debris flow initiation induced by rainfall and snowmelt. In his recent works, he has been focusing on understanding the hill slope hydrology of shallow landslides and debris flow to develop thresholds for early warning systems at slope scale and catchment scale. He has worked in the development of real-time landslide early warning system in Japan, and is currently in the process of employing the same in the Indian Himalayas. So over to you, Dr. Krishnan.
Thank you, Swati ma'am, and thank you, DRRF, for inviting me to this webinar, Resilient Talk, and thank you for this opportunity, and thank you for the kind introduction as well. So let me share my screen first. I hope my screen is visible and I'm audible.
Yes, very much.
Thank you. So, good morning, all audience. And as part of the landslide mitigation measures and strategies in today's webinar, I'm here to introduce a territorial scale landslide early warning system, which we are currently developing for the state Uttarakhand in India. If we remember, landslides are not new to our nation, India. Like last decade, there was the 2013 North India flood, which also has triggered widespread landslides, both shallow landslides and debris flow, all across the catchments of Uttarakhand, including the Kedarnath catchment. In 2018, Kerala experienced 1 in 100-year precipitation events, which also triggered more than 4,000 of landslides all across the major river basins of Kerala, including the longest river, that is the Periyar River. The photographs what you are seeing are like few images of those disasters. You might have come across these images many a times in research articles, newspapers, and other sources as well. In 2018, even Kerala, when it experienced the extreme rainfall, there was widespread disruption for the entire monsoon period, starting from 1st July to let's say 15 August. And during this time, the impact of rainfall was actually on a compounding and cascading mode. There were widespread shallow landslides took place within the 2 months. There was also flooding happened, and then the materials which got produced in the hill slopes as shallow landslide got transported to the rivers as debris flow. So the impact has really compounded, and then the widespread infrastructure disruption has been taken place. Very recently, we all aware about the Wayanad debris flow disaster that happened, and it has caused many number of fatalities, casualties, as well as economic disruption. This is also an extreme rainfall-induced event, which actually acted on a larger scale. By looking at these events, if we understand, at some place the landslides are happening at like one or two major landslides, whereas the few other events in the historical past, such as the 2013 one, the 2018 one in Kerala, and I didn't mention here the 2023 North India floods in Himachal also has caused widespread landslides and debris flow activity. If we look into the scale and range of analysis for landslide studies, what we experience, what we can visually see is from the 10 to the power 0 meter scale to 10 to the power 4 territorial scale. Whenever these extreme events are happening, more number of landslides are happening at the same time. Maybe not exactly at the same minute to minute time, but maybe within a month or so, many number of landslides are happening. So we need to have some kind of system for landslide mitigation, which will warn us before the landslide happens. So that is at the territorial scale. So we need early warning systems at the territorial scale, or we can even call it at the regional scale. To have the early warning system, the landslide mitigation at this territorial scale, we need to have a proper understanding of the catchment scale hydrology. So that comes at close to 10 to the power 3 meter scale, that is the catchment scale. Whereas if we go to each and every landslides, at each and every landslide at the slope scale, it's also unique based on the type of the landslide as well as the mechanical and hydrological characteristics of the landslide. We need to understand them at the slope scale also. How we will understand at the slope scale? In case of mechanisms, we have to bring samples from the slope to test it in the laboratory, which we do it through reduced scale experiments to understand the mechanism. Our research group in IIT Roorkee is actually working across these scales to produce an early warning system at the territorial scale, which will be helpful during extreme events to warn the people before a landslide happens. And also there is mesoscale landslide studies, mainly on the biogeotechnics. Few landslide scientists across the globe have already begun working in this research aspect, in which few like bacteria has been introduced, which actually stabilizes the slope. Whereas our focus are between the scales of, let's say, 10 to the power 0 meter to 10 to the power 4 meter. Okay, these landslides are happening in abundance of number at the scale. What to do about it? We need to understand the physical processes that leads to landslide. Let's say, for example, rainfall-induced landslide. Whenever there is rainfall that happens on a hill slope like this, we do have vegetation cover and we do have thick debris cover that is mantled on our hill slope. And then this rainfall that being supplied to the hill slope infiltrates and then move as a wetting front. Slowly it will reach the groundwater table. Whereas above the groundwater table, we have the unsaturated part, and below the groundwater table, we have the saturated part. And when this unsaturated part becomes saturated, then a line of failure here develops, and this will behave like a shallow landslide. And if there is excess amount of infiltration exceeded runoff, then there is a chance of debris flow. So in all these extreme events which we have seen in the previous slides, two types of landslides were common. One is the shallow landslide, which is actually a slope failure. And then the next is the debris flow. The debris flow, because of the surface runoff, it travels to longer runoff distances so that it impacts or moves. To have an early warning system which will inform us before this landslide fails as well as before the debris flow happens, we need to have systems that is operating at the territorial scale, that is more than like 10 to the power 6 meter scale. If we look into the global knowledge, the scientific rationale of early warning systems across the globe, we could see that two type of meteorological thresholds were being used as shown in this sketch. So there are different countries which is marked in like blue color boxes, which uses the intensity and duration of rainfall as a meteorological threshold to give the warning before the landslide happens. There are also few other nations which are using complex threshold, which also include the terrain condition, that is also the hydrology of the hill slope to give the warning. So these are hydrometeorological thresholds and these are meteorological thresholds. Here also we have three systems that is existing in India. One system is the ISRO's experimental early warning system for rainfall induced landslide, which is currently being as an experimental prototype along selected road corridors in Uttarakhand. Our work is actually in this system, which I will come upon in the following slides. Very recently, Geological Survey of India has also started their National Landslide Forecasting Center, headquartered in Kolkata. But they have like warning sites for Uttarakhand, Kerala, as well as Darjeeling, and few other places as well. At few places it is operational, and then at few other places it is experimental. Very recently in Kerala, Kerala University Group uh, has developed a landslide early warning system and also an Android app that is known as SlipK. This is also being operational, starting to get operational at few places as well as it is experimental. With regard to the Indian case, the first case that is the ISRO's landslide early warning system, which is an experimental system in Uttarakhand. So along selected road corridors, you can see here, this system is actually established. This system, unlike many other similar systems across the globe, is based on the meteorological threshold, that is the quantification of rainfall in terms of intensity and duration. So this is the database and this is the threshold curve. Once we have the rainfall forecast from weather agencies, usually all these early warning systems get the weather forecast from weather agencies. For India, it is the India Meteorological Department. And once that weather forecast is there, so they check whether the intensity and duration is exceeded, then the warning is given. If it is not, then the warning is not given. Whereas the problem with Indian cases is we do not have a strong database of historical rainfall-induced landslide events so that we can easily identify the threshold between the intensity and duration. For this, at IIT Roorkee, we have come up with an approach to synthetically simulate these landslides which happened in the historical past and then analyze the debris flows and shallow landscape. So this is our numerical modeling strategy. So we have developed these numerical models using the concepts of catchment scale hydrology as well as geotechnical mechanisms, including saturated and unsaturated seepage characteristics. And we have deployed them at the catchment scale. So the test area, our study area is Uttarakhand. As such, the existing system of ISRO is also implemented in Uttarakhand. So at first we have done some fieldwork. We have taken the Kedarnath catchment. We moved with a smaller study area. We didn't go with the entire road corridors. At Kedarnath, we have done our fieldwork to collect the samples for material testing to know the properties of the landslide material. Once that is done, we have developed the numerical model and we have tested our numerical model for the 2013 North India flood case, choosing Kedarnath as the study area. As you can see in this figure, this is the Kedarnath catchment. Gaurikund is here, and then the Kedarnath temple is close to here. And the red polygons or landslides, these landslides are mapped by National Remote Sensing Center, and then the data is also from National Remote Sensing Center, ISRO. So this inventory shows 120 landslides. Most of them are debris flows which happened between 3 days during the 2013 North India floods. So 120 landslides happened. But we do not know under what intensity or duration threshold these landslides got triggered. The main reason is we do not get much higher resolution weather data, observed weather data at this scale, and we do not know the timing of the landslides, exact timing of the landslides in which it get triggered. To overcome this challenge, our numerical model actually runs over this catchment with the material properties that is being tested from the lab with the collected samples from the site. And once this is done, we actually simulate the landslides using our numerical model in order to see under what time and under what intensity and duration thresholds these landslides got triggered, so that we are actually strengthening the existing early warning system. And this is the meteorological flowchart. So here also we use a atmospheric sciences weather research forecast numerical model to get the forecasted weather rainfall. But since for this case, this is a historical case, it was run in a hindcast mode. Once the data is there at high resolution, then the debris flow model runs at a finer resolution timescale. So the DEM resolution, what we have used is 12.5 meter by 12.5 meter. And then this model actually produces debris flow. This is the WRF model configuration, which we have used for our study. And once we get the WRF model rainfall, it is also compared with the historical satellite-derived precipitation. We do not get much accuracy of the precipitation compared with the satellite-derived precipitation. The problem here is the WRF model actually overestimates the rainfall, whereas the GPM usually tends to underestimate. So that uncertainty is still here. And then the numerical model is run. As you can see here, these are the debris flow deposits from the model, and these are the landslides that was mapped. These are the mapped landslides from the inventory. So we had an accuracy of up to like 60%, and most of the debris flows which happened in the catchment during the Kedarnath disaster has been produced from our model, and also there is some uncertainty, means false positives are also there. We could generate the volume of landslides, which actually got triggered in the Kedarnath catchment with the measurement, empirical measurement from the literature data. And once this model is calibrated, we then rerun the model with the different intensities of rainfall to get the intensity and duration threshold. And this is the intensity and duration threshold, which was actually obtained for the Kedarnath catchment. While comparing this ID threshold with a similar hourly rainfall-based intensity and duration thresholds of Uttarakhand state, so our model results actually sits here. With this, what we have done is we are actually adding additional data points to the ISRO's existing system so that this threshold can be improvised. So far, we could add it for one case study, that is the Kedarnath case, Kedarnath disaster that happened in 2013. For that catchment, we could find the curve, and then we are updating the existing database of ISRO to improvise the intensity and duration threshold. So this paper is actually, this work is actually published in NHCSS paper. You can see the reference here. For now, we are going with 5 kilometer by 5 kilometer grid in Uttarakhand, and we believe this will actually improve the predictive capacity of the existing system. And also additional hydrometeorological threshold, which are currently under development and testing for this system, to improvise this into the existing ISRO system. So, while summarizing this work, the objective was to develop landslide mitigation strategies. So, at the territorial scale, territorial scale, it is always a non-structural mitigation measure. That is the early warning system, which will aid people for evacuation. So, we combine the use of physics-based models. We developed our own physics-based models, accounting for the catchment scale hydrology as well as the geomechanics, through in situ testing and laboratory testing as well. And then we generated synthetic landslide event under different scenarios to get the early warning thresholds for data scarce region. And we strongly believe this approach will also be applicable to other steady areas where a new year or a very empirical early warning system has been established at the territorial scale, and we want to improvise the thresholds. So this approach shall be used in those areas as well. So with this, I thank DRRF and Swati ma'am for this opportunity, and thank you all for being patient to listen to me. So I'm also open to questions and discussion as and when it is allowed by the chair. Thank you very much.
Thank you. Thank you, Dr. Krishna. It was a wonderful presentation. We'll take up the questions in the end.
Okay.
So let's hear all the other speakers at this moment. Next speaker is Dr. Parvati. She is a scientist, principal scientist at CSIR, Central Road Research Institute in New Delhi, where she does the research and consultancy on geotechnical engineering of roads and highways. She has received her BTech degree in civil engineering from College of Engineering, Trivandrum, and MTech degree from IIT Kanpur and doctorate from IIT Delhi. Her experiences include leading over 26 research and industry-sponsored projects related to the characterization and application of geomaterial, including geosynthetics, geofoam, and marginal materials for ground improvement. She has published papers on various case studies of ground improvement techniques and marginal material utilization for the construction of road embankments. Two of her papers were conferred with the Best Paper Awards, such as the IRC Medal and the IGS Ferroco Young Geotechnical Engineer Award. She is also the recipient of IGS Delhi Chapter Young Geotechnical Award and IGS Forensic Geotechnical Engineering Award. So over to you, Dr. Krishna, Dr. Parvati.
Yeah, thank you, Mukta ma'am. Thank you, Swati ma'am. Thank you, Dr. Mukta, for the invitation. So I think I will focus more on the remediation aspect of road infrastructure, which is what we have been dealing with in our institute, rather than the early warning or overall aspect of landslide. So I hope it will be useful to design engineers who are dealing with the remediation aspect. So I'll share my screen now.
Yes, ma'am.
Yeah. So, so hill roads, actually, I will cover the problems and some of the case studies so that the talk will be more interesting rather than going to the basics of the design, basics of this hill roads and the problems. So hill roads, actually, everyone knows that when the terrain cross-slope along the of the slope is between 25% to 60%, it is called a mountainous terrain. So when we construct a road across that, it is risky. But if the cross-slope is more than 60%, we classify it steep hills. So whatever it is the case, we have seen failures for both the cases. So yeah, majorly these kind of failures are occurring due to the poor drainage or sometimes the poor design also it is there. So the problem with hill road is it is costlier to construct compared to plain roads. Just imagine if for 1 kilometer, the cost of construction for roads in plains is 1 crore, then it goes to 10 crores for the road construction in hilly terrain. So, but the problem is that many of the agencies are not giving proper importance to the detailed project report preparation before the start of the project. So whether it is a new road construction or whether it is a widening of the existing road. So proper design, proper focus needs to be done in the detailed project report, DPR preparation stage itself. So that is why many of the hill roads nowadays constructing are having some litigation problems or between the contractors and client. So CRRA has been brought in many cases to solve the problems. So, and the major problem with the hill roads is it is prone to more accidents. There is a width restriction. That is one of the major problem because we can't take up the ROW will be very much limited. So we have to limit everything: the shoulders, the main road, carriageway, and the retaining structures, everything between that ROW. So that is a very challenging task for a design engineer. And also there are frequent hairpin bends, corner bends, and there are site distance restrictions. And another problem is surface drainage. These are our main features of the hill roads. So when we construct a hill road, the major thing is that we are intercepting the natural drainage. The water will be flowing along the hill, so we are intercepting that drainage. So sufficient precautions needs to be taken so that this natural drainage is not intercepted. So proper design of culverts, cross drainage, or trench drain, these all things are necessary. However, in most of the case in Indian case studies, the problem is that fund restrictions will be there, proper DPR preparation may not be there. So these all lead to the a poor design and poor implementation of the project. So when we talk about highways only, highways means the national highways. When I collected some data from NHI, DCL and NHI, we can see that more than around 4,500 kilometers of hill roads are right now in the planning stage, and around 2,000 kilometers is under construction. So most of them are with respect to the NHTP projects. So you can see that NHIDCL has contracted many stages, like many states like Arunachal Pradesh, Manipur, Himachal Pradesh, Meghalaya, JNK, Nagaland, etc. Whereas NHI is still handling some of the projects which they have been taken from very long, much like 10 years back and all. So like mostly in Himachal Pradesh, JNK, Karnataka, and Meghalaya. But nowadays, most of the hill roads are being constructed by highways is being constructed by NHIDCL. So the problem which we have seen during the design is high intensity of rainfall. That is one of the major problem. And there's a difficult topography. And every 50 kilometer, sorry, every 50 meter or 100 meter, the terrain will be changing. The cross slope will be changing. So that is a difficult topography. And so the uniform design may not be possible. However, in the DPR stage, there might be, for a 20-kilometer stretch, there might be 10 cross sections. So the implementing contractors also face the problem that difficult constructing in that changing topography. And second is continuous gradient of the road. When you see, as per actually in ideal case, there should not be any water flowing through the road. But when we see in hilly terrains, we can see water is flowing along the road. So the cross slope, giving the cross slope and gradient is very much important. And the another thing is moisture subgrade. There will be subsurface seepage flow from the uphill slope. So that also weakens the payment layers. So then uncontrolled water creates problem for the road. As I told you, in many cases, when I travel in Kerala and Tamil Nadu, we can see that water will be during the monsoon gushing through along the road. That means drainage has not been properly given, or it has not been designed for the current ever-changing climate change. Because of the climate change, there is a heavy rainfall happening. So it is not, most of the roads are not designed to carry that much water, surface as well as subsurface seepage. And one of the key aspects during the hill road design is controlling the water. So whatever problem we have faced in, most of the time CRRI has been brought in to solve a problem. So whenever there is a landslide problem, we have been brought in to remediate the problem, design the remediation, or see why it is failed. So 99% of the case, we have seen that it's majorly due to the water problem. So I will cover two such case studies and how we have tackled that problem and how we have remediated that problem. One such case is along the Kerala-Tamil Nadu interstate highway. When we go from Nilambur to Ooty, so there is a forest area which is called Nadugani area, Naduganishwaram. So during the 2019 August, there was a very heavy rainfall in Nilambur area, which has led to the Kavalapara landslide, which is which has caused a lot of casualties and all. So around 20 kilometers away from that Kavalapara, this is along the highway. Luckily, the problem is that the thing is that this area is located completely inside the forest. So there is not much habitation is there. So, but the problem is that this is the only road connecting the Kerala and Tamil Nadu. Otherwise, they have to roam around still through Wayanad and all. So that highway has been blocked in 4 locations. 4 locations there were landslides. So they couldn't, the traffic was completely stopped for more than 10 days. So there were, in two places, there were rockfall. And the two places, one is rock slide, completely it is a rock slide, and one is rockfall. And another two cases, second, third cases is slip failure, slope instability. That will I will be covering in detail here. And the fourth case is due to the seepage issue. Because of the seepage, we can see water is bubbling up from the pavement layers in between the cracks. And there were failure of retaining wall. The thing is that this road was a single lane road constructed during the British period. In 2018, it has been widened from single lane to double lane. So construction was done properly, there was no issue. But throughout this kilometer entire stretch, the contractor might miss some of the other things because left side and right side is forest area. So they can't encroach or they can't go into the forest area to investigate further. So when we went there, there were problems. We couldn't find out what is the problem. For a particular stretch, around 200 meters, as you can see, around 2 meters that road has been settled. One of the carriageway has completely washed away, as you can see. Yeah. And almost the first lane, which was constructed prior, was also damaged. And as you can see, almost around 100 meters has settled more than 0.5 meter. So we couldn't find that the problem because only for that stretch only this much devastating failure of road has happened. So when I went to the study, because it was a very sensitive area because people wanted to travel or most of the traffic is in blocked. So we were roped in. So when I went to the site, when I went to the uphill side, even inside the forest, at that time we could see, I went in the night time, but still I could see a very big pond in the uphill around 60 meter high. That pond, as you can see, I have demarcated in the plan area. That pond is an unlined pond, which is not designed by anybody, but it has been provided by the forest for drinking water for the wild animals. So animals come there in the evening time, elephant and all, they come and they drink water. So because of this pond, the water, the failure has happened just after the heavy rainfall, not during the rainfall. Highest rainfall has happened around August 8th or 9th. But after around 10 days only, this problem has happened. That is because the subsurface, all the uphill slope is getting saturated throughout these 6 to 10 days, which led to the failure, sequential failure of this road. As you can see, this is the cracks. There was a retaining wall here. Retaining wall has completely damaged. So this is a Google Earth image. As you can see, it is existent. The road goes along the curvature. So this is the affected stretch. There is a pond over here. This is from where the water seepage has happened along this way. I hope you can see my this mouse cursor. Wait.
Yes, ma'am, we can.
Yeah. So along the this side, the water passage, water subsurface flow was there, and subsurface flow went till around 5 to 6 meters deep. So there were culverts. The culverts were designed properly. There were no issue, but the problem is that water has been going beneath the culverts. So that this is a pond, as you can see, which is more than around 3 meters deep, where these animals used to come in the even the evening and all for drinking the water. So these are the pictures of the damaged retaining structures. So there was a retaining structure, and to increase the height, they have given a cantilever retaining wall above it. That was also it's a problematic. So what we did that we wanted to know how much soil is saturated. Subsurface flow has been happening till which depth. So what we did was we did a geophysical method, electrical resistivity test. This is for the uphill from the road till 60 meter above. So you can see this whole downhill that near the road area is saturated, and along the downhill starts from here from the road to down. As you can see, till around 20 to 30 meters, it's completely saturated. So we have done the slope stability analysis by limit equilibrium method. And then we have done the technical investigation and geophysical investigation, and then a seismic refraction test to study the surface layering. And then we have checked that whether it is safe or not. As you can see, during the rainy season, the factor of safety is going to be being critical. We need a factor of safety of 1.3, but it is going between 1 and 1.1. And during the dry season, it is safe. So what we did was We have given, this is a road area. What we have given is that this is an uphill slope and this is a downhill. To collect the subsurface flow, we have given a this deep trench drain. Deep trench drain is a trench which can be constructed using JCB and which will be infilled with the gravels. So, and then we'll be collecting we'll be taking away using a perforated, semi-perforated PVC pipe, which will be connected to the culverts to take away the water. So, our main purpose is to make this area dry so that this should not affect the road. That is the main thing. So overall, the slope is stable because the uphill slope is ranging between 15 to 20 degree, and the downhill is also in the range of here just nearby that only around 40 degree. After that, it is gentle slope only. So overall slope is stable, but in and around this pond and the road has been unsafe. So we have given deep trench drains and gabion walls here. Gabion wall is porous structure, and then the soil nailing. So all along this around 100 and 150 meter stretch length. And we have given intercepting. You can see yellow drains. This is cross drainage. Just like the trench drain here, we have designed a cross drainage to take away the water in any case if water is trapped beneath the pavement layers. So then we have checked it and we found that the slope is becoming stable even in the high rainfall season also. Now I will come to the case study 2. Second case study is in Madhya Pradesh, which is when we go from Nagpur to Chhindwara, it is nearby that area, but it falls under Madhya Pradesh. But this project has been very close to the minister because it is near the home state. Here the problem was again the same. One carriageway has been washed away during the monsoon. During the 2019 monsoon. Then the main funny part is that this been already been designed for with a gabion wall, just like we have given earlier by the contractor during the previous summers. It has been keep on settling, so they have already given the gabion wall. When we were roped in, this gabion wall also has been damaged. See, as you can see here. So this gabion wall, which was designed by the contractor, has been already been bulged and failed like this. So and the thing is that the uphill slope is intact, but the downhill slope has been, see, the tree has been toppling like this. So as you can see, it is causing erosion. The top soil is moving downwards. That is the main problem we have assessed. So this was when we went there, there were already halfway in construction. There was a geotextile filter, gabion mattress, gabion wall, which was already there and which is already failed. Within 6 months, it has failed. So again, what we did was, you can see the settlement over here. Again, we have gone to the geophysical investigation because within a day, geophysical is very easy to do. Within a day, we can cover many as high as 2 to 3 kilometers stretch length of this geophysical survey, SRT and ERT. So we have conducted that and we have found out how much layering is there and what is the topsoil cover thickness and how much is the saturation. All these things we'll get from the geophysical methods. So this is the geophysical test result. This is ERT test result. As you can see, the downhill slope where it is saturated. This is one line along the downstream. This is second line along the downhill slope. And this is SRT where we can see the top layer overburdened soil thickness. And this is second layer is highly weathered layer. And third layer is moderately weathered and then followed by the hard rock layer. So, and then we have measured the rainfall for that area. And then we have conducted a more advanced analysis with seepage coupled slope analysis. That means first we will be doing the finite element analysis, how the seepage is affecting the slope with respect to time. And then we find out what is the maximum pore pressure generation and what is at what time, which month. And then we will analyze the slope for that rainfall. So we found out that the factor of safety is less than 1.3. This is a degree of saturation. As you can see, so all throughout the downhill slope is giving the red color. It is highly saturated. So, and this is the pore water generation. There is a pore water generation is also high along the downhill slope. Around 60 to 100 meters, this pore water pressure generation is there. So what we did was, we had two options, either to demolish the gabion wall and reconstruct a new gabion wall, or remediate the gabion wall, or reconstruct as a new soil nail and shotcrete wall. But the client has opted for this one, gabion wall remediation. So whatever the maximum damaged portion gabion wall, they have removed, and this has been retained as such. And then we have given the soil nails. Because why soil nails? There are many other options. There are reinforced earth wall, there are breast wall, but soil nail is the cheapest solution possible. As you can see, we have adopted a composite remediation technique. This is we have divided the slope into 3 tiers: tier 1, tier 2, tier 3, and tier 4. 4 tiers, and then for each 4 tiers, we have designed with varying soil nails of length, dia, and spacing. And along with this, the soil nail can't act alone. Either we need to give a shotcrete, or we need to connect the each nails with some steel mesh. So if being in a forest area, we can't give a shotcrete all throughout this much area. So we have opted for the given wire mesh to connect the soil nails. And along with that, we have given some subsurface drainage. So what we did for subsurface drainage is we have used perforated pipes, semi-perforated pipes, and drilled it all along the slopes wherever the maximum saturation we have observed, and then collected it along the at a particular gradient and collected through the catch water drain and to the downhill side. So these are some of the pictures of this implementation of this remediation measures. As you can see, this kind of wire mesh has been given. Wire mesh we did not affect the vegetation. We didn't recommend any cutting of trees, so they could implement that measures without any problem. So this is the process of drilling the soil nailing. Soil nailing can be done with very, like, it is very easy to construct even for a steep gradients also. This kind of machine can be used for soil nailing. Has been recommended for steep hilly terrains. So that's all. I think these are the case studies I have covered. I think this at least some insights, somebody might have got some insights into how we remediate the problems once a landslide happens and affects the road infrastructure. Thank you, ma'am.
Thank you so much. It was a wonderful presentation. I didn't know really the roads are very important part, especially in the hilly area when we talk about a landslide prone zone. So thank you so much, ma'am. And may I now invite Dr. Hemlata. Dr. Hemlata is an assistant professor Amrita Vishwa Vidyapeetham Amritapuri. She is an accomplished researcher with a deep passion for advancing disaster risk reduction. She is primarily engaged in research focused on forecasting imminent landslides, leveraging social media analytics for natural hazard event detection, and developing decision support system for landslide monitoring and early warning. Her work centers on establishing sensor thresholds for landslide forecasting, enhancing the accuracy of imminent landslide predictions, and conducting risk analysis. Her areas of expertise include data science, machine learning, computational optimization, disaster risk reduction, and multi-hazard modeling. So over to you, Dr. Hemlata.
Thank you, ma'am. Thank you, Swati. Can you hear me well?
Yes, we can hear you.
Sharing the screen, and thank you for the opportunity. Hope my screen is visible.
Yes, ma'am, it is.
Okay, so today my presentation is mostly aligned on the topic of the discussion, landslide mitigation measures and strategies. In this topic, I would like to discuss about what are the landslide mitigation activities that we have done, and how successful we are in at least 2 places where we have the system. And before starting, I would like to introduce our Chancellor, Sadhguru Sri Mata Amritanandamayi Devi, and she is the motivation behind such a research. And she actually encourages us to take the research in a compassion-driven manner and make use of the research to serve the lowest and most vulnerable strata of the society. And so that's how we are driven. And so briefly, I'll discuss about the landslide scenario in India. In India, as we know, we have varied topography, climatic conditions, agriculture, mineral resources, flora and fauna. And approximately 12.6% of India's land mass is prone to landslides. And we have two landslide hotspots globally. One is the Himalayan arc and one is in the southwestern coast of India. Both the two landslide hotspots are in India. And so India needs more of landslide research, and India needs more of landslide mitigation activities than any country. And so here I'll briefly talk about the AI-enabled IoT-based landslide monitoring and early warning system. And we haven't stopped with the technology. We have also included the societal aspects to the early warning system, integrating crowdsourcing and community resilience. So I'll briefly introduce about the system that we have, and also tell about the success stories, how we were able to avert disasters and how we were able to mitigate in the areas that we have the deployment and monitoring. So we have at present two deployments. One is in Sikkim and another is in southwest coast of India, in Kerala, Munnar. And in these two places, we have something called intelligent wireless probes, which contain several geotechnical sensors, and they are installed under the ground, and they sense the system 24/7, and they transfer data to us. And we have also established intelligent algorithms in the nodes itself, in the ground sensing nodes itself. And we also have developed artificial intelligence algorithms on the cloud levels, where we will be able to understand the risk that is proceeding, and we'll be able to do early warnings. So here is the system in Munnar. So you can see this is the hill that had landslides in the past, and there's a settlement here. And we have developed site-specific and regional early warning from the measure thresholds, the such things. And we successfully give early warnings to this community. In this year, 2004, also we gave 3 early warnings so far, on an June 26 and another in July 15, and one more date. So here are the deployments we have. We have several deep earth probes, and we have a system that captures the time sense measurements from the subsurface on real time, and it sends to the university here, where we do the data analysis. And this is how it goes. We have geophones, pore pressure sensors, strain gauge sensors, moisture sensors, and rain gauges, and wireless interfacing circuits, and an antenna. And this is a system in Sikkim. And yeah, so we have come up with analysis with respect to rainfall, and analysis and rainfall thresholds. And these are some of the analysis that we have done. We have analyzed moisture and pore water pressure over the years, and we were able to quantify the amount of pore water pressure for a amount of rainfall, and based on that we were able to do the forecasting mechanisms. Here are some pictures from them. And we were also able to identify the slip zones in our area using geophysical measurements in collaboration with the British Geological Survey. And here are some pictures from it. And we were also able to find out how much the inclination variability, like the movement that is happening in the soil through strain gauges. And here are some of the decision models. Here are some of the rainfall threshold models, and these are the models that we use for giving warnings. And here is one particular thing that I would like to mention is we have done forecasting of the vital parameters like moisture, pressure, etc. under the soil. And then one place where we were able to achieve reliability in the system is especially in the during the 2018 landslides, there was a power cut, and the system wasn't functioning the system was at low power levels, and we had to maintain the system for giving warnings. So because of the 2018 floods, the road was cut down, the power was cut down, and the city was without power for more than 7 days, and the solar panel power is also less because of the clouds and rains. So at that time, when we are in need of data, when we are in high demand for the data, we are not able to build the data. So at the time, our forecasting algorithm helped, and even during such times when the system was completely off, we were able to give warnings with the forecasting algorithms that we have developed. That was one of the success story, and we were able to accomplish reliability through the intelligent data acquisition algorithms, like extending the system for a longer period of time by reducing the sensing rate. The edge node itself is intelligent, so it looks into the power level, it looks into the remaining energy and adjusts its sensing rate and tries to prolong its lifetime. So like that, we were able to have a reliable system working for longer durations and also accomplishing reliability through machine learning algorithms. In the absence of data, we were able to use the minimal data that is available through satellites and other products, and we were able to give warnings. So this is a screenshot from the real-time data visualization. And we have a multi-level warning system. We have first level warning, second level, third level, and fourth level warning. And these are based on rainfall thresholds, the first level warning. And the second level warning is based on rainfall thresholds and moisture thresholds and pore pressure thresholds. And the third level warning is based on the dynamically learned stability parameter and all the other parameters, including the first and second level warning. And the fourth level warning is majorly based on movement and vibration threshold. And the first level warning comes to the researchers, and the second level warning we take it to the government. And after that, it is taken to the media and to the public. The government takes it basically to the media. So here are some of the landslide early warnings that we had issued over the years. We issue warning letters to Kerala State Disaster Management Authority, the collector and sub-collector of that area. And they call the firefighters and the police. And then even this year, the people were evacuated from our community to the places nearby in the camps, and they stayed in the camps for pretty 2 weeks. And then after the rainfall level have reduced, they came back to the home. That's how we averted a disaster. And this is one of the, to help in this process, we have developed an app, and this app is Landslide Tracker app. This was developed along with the Landslide project, along with other partners, other 9 partners in the community. So this app will be able to track the landslide. The users can input the landslide, where the landslide had happened, and it's available in many different languages and so on. This app is being used by the community people. We had given training for them to use this app, and that's how we also get inventory for the landslides from the community itself. So the community helps the community, and the community helps the researchers. So landslide doesn't stop here with the technical aspects that we are that most of the researchers are eager to. Landslide has a bigger impact on the local community. We have spoken with the people in the community, and it is really a first experience that you hear from the people. They live in trauma, they lose their lives, and they lose homes, they lose they lose the job opportunities that they had earlier, and so much other things. So actually, the landslide mitigation strategies or the landslide research needs to be focused on the societal impacts also. Otherwise, finally, the end user is the people. And if the research is not carried to the people, and then the research has less importance. So we have tried doing that, and we have interventions and success stories from that. So we have provided community risk awareness programs in the deployment sites, and we have educated on the landslide precursors, means educated the people, the school children, the community leaders, the primary health workers, and the adventure club members and any volunteers on the landslide precursors, and how they can be aware of the area that they are living in. And we have trained school children for doing that, and they are very eager to do that also. And these are some of the snapshots from the capacity building workshop that we conducted. And we provide general guidelines to those who are living in the landslide prone area. And we educate them not to the do's and don'ts of whatever when they are living in a landslide prone area. So these are some of the pictures from the education that we provided to the community. So we asked them to look if they have any cracks in their homes, and then if we also ask them to look if their doors are getting jammed during the the monsoon season, and so like that. So this is one snapshot from the community where we are working on. And we are also asked them to look for if there are any fractures they are noticing on the ground. And we also asked them to look for the water levels that are increasing in the wells, and see if the trees are, if they are finding any sudden tilting of the trees in their locality. If there are any tilting of trees and tilting of poles or soil ripples, fence out of alignment. If they are looking at any of these, we ask them to alert it in the group. We have a WhatsApp community group. We have WhatsApp community, and people are very active there. Even both the researchers and people are active there. They give all those informations, and then and we ask them to let us know if there are new springs or new saturated grounds which was previously not wet. So such are the things which we ask them to monitor and update to us also, movement of soil away from the foundation. And if they are hearing any unusual sounds like tree crackling, bow or knocking, rumbling sounds or vibrations. And encouraging, we also encourage the community, especially children in the community, to do simple things at home. One is to measure the rainfall, know your rainfall measurements, know the amount of rainfall that you are getting at your locality. So they measure using simple bottles, and then like a 24-hour reading, they measure, so they know whether the rainfall amount is increasing or not, and we ask them to upload it in the group, and they do it very actively. And also they measure the cracks that are happening in their ground. And these are some of the snapshots from children. And these are some of the newsletters that came up, and this particular one was today, that our landslide work has been mentioned in the United Nations blog on COP20. So this is how we have been averting disasters in two locations in India. So I would like to conclude with the lesson that we have learned over the years. There's an importance, there's a critical need for early warning systems all over the India. And even if the warning systems are in place, the community needs to be educated. The community and the people at the low level needs to know where they should be building a settlement, where they shouldn't be. Is this a drainage path? or is it safe for me to build a home here? How much is the rainfall that has been happening? Is it okay for me to stay in this particular location if the rainfall had crossed this much amount? So a basic knowledge, basic education, a community member, each and every people in the community needs to know. That's the only way we can mitigate landslides in a large country like India. And this is our landslide team. And Dr. Manisha Vinodini Ramesh is the director, and she's been directing the landslide research since 2006. And this is a team photo with our chancellor, Sadhguru Mata Amritanandana Devi. And I would like to end by saying one of the quotes from our beloved Amma. Today, universities and their researchers are ranked mainly based on the amount of funding they receive, the number of papers they publish, and their intellectual caliber. But along with this, we should take into consideration how much we have been able to use research to serve the lowest and most vulnerable strata of the society. In our approach to sustainable development, we should not forget that it is by strengthening the people at the base of the pyramid that the entire edifice to the society grows healthy and strong. Thank you.
Thank you, Dr. Himlata. It was a wonderful presentation, giving an insight of the usage of modern technologies for the mitigation purposes. And specifically, when you also mentioned about engaging with the community, that is also very, very important because if the community awareness is there, I'm sure most of the things, maybe the pre-disaster and the pro-disaster can be reduced. Implications could be reduced. So thank you very much for your wonderful presentation. Now I would like to invite Dr. Sansar Raj Meena. Dr. Sansar Raj Meena is assistant professor in the Department of Geosciences at the University of Padova, Italy, and he is also a visiting scientist at the Center of Remote Sensing at the University of Boston, USA. He holds an MSc in Geoinformation Science and Earth Observation from ITC University of Twente, Netherlands, and a PhD in Applied Geoinformatics from the University of Salzburg, Austria. He specializes in AI, remote sensing, GIS applications for natural hazards. So over to you, Dr. Sansar. Dr. Sansar, are you there?
Can you hear me, ma'am?
Yes, we can hear you.
Okay. Thank you so much for the invitation and for the introduction. Let me share my screen. Can you see my screen?
Yes. Can you put it on the full? Yeah.
Yes.
Thank you.
Thank you. So I will be talking about a little bit different from other speakers. It's mostly about how we can map landslides more automatically. So I will just talk about the problem of landslides, mostly in developing countries, and then what we are still missing, and then what are the problems that we have, especially for mapping landslides, and how machine learning, deep learning can help us. So just to give you an overview, I just want to talk about this. As you can see, this is if you look at my mouse cursor, these are potential landslide activities globally. If you see, most of them are, of course, in the mountains. And then most importantly, if you see, the most of the population which are affected by these lives in Himalayas. So my research have been mostly on Indian Himalayas, India, Nepal, and also in Western Ghats. Now I work in Italy on many areas in Italy and also in globally. But to point out The most important thing that I want to point out here is most of these like landslides, they affect people because still we don't have a good mechanism in place for landslide management. If you look at the number of landslides and also the number of deaths in comparison to other developed countries, like mostly in Europe or in USA, or the number of deaths is a lot in India, let's say. And to improve all these and to better understand the landslides, we should know where they are happening or where they have happened. So this is what I have been doing for last 5-6 years. This is an example of if you see how big the landslide prone areas in India, this one. So in India, we are still trying to do national susceptibility mapping. So there, first, before starting anything, I want to clarify, because in literature, there are many, the terms like mapping, susceptibility, hazard, and risk. These are used interchangeably most of the time. And in order to understand the whole process better, we should know that landslides are, they can be mapped by using detection algorithms, but susceptibility and hazard are two completely different components. Landslide susceptibility is spatial likelihood of a landslide happening in an area. But if you look at the hazard, many people in India and also in globally in publications, they use these terms interchangeably. And so we should make a clear distinction between susceptibility and hazard. Hazard, what is the main difference is the temporal component. If we know when a landslide can happen and where, then is an hazard. But if we just show a probability of a location of a landslide happening in an area, it's just a susceptibility. And then risk is another component. So if this is clear, then we can make much better approach or make much better decisions to deal with such problems. So landslide inventories. So landslide inventories, why, they can be done for a single event. For example, now recently in Kerala, there was a landslide which it was a single event. It was a single landslide event, but there can be many landslide triggered by an earthquake event or rainfall event, like what happened in Japan, also in 2018 in Kerala or in Karnataka. There were many landslides triggered. So mapping these landslides is sometimes very difficult because they can be triggered by earthquake or rainfall events. There can be many landslides at the same time. So why do we need these inventories? Why we need inventories? Because landslide inventories, they are the main core basis of the next steps. Like if you want to do susceptibility, hazard, or risk, or if you want to train AI models, you need a robust inventory. That's why my focus has been to improve the landslide inventories. So if we know the past conditions of an area where the landslides have happened, we can try to understand the spatial likelihood of where landslides may happen in the future based on the conditioning factors, which is called susceptibility. But as I said, landslide inventories, they are often used to validate hazard models or susceptibility models, and even validate nowadays a detection algorithm to automatically map landslides. These are some of the examples of manual mapping, where same area three different people map landslides, but they map them completely differently, as you see, because this is a very subjective issue. Like as a human being, our understanding of one particular subject can be different, and we need to understand this very carefully, that this subjective issue can create a lot of problems if we want to do susceptibility or hazard assessments later on based on this kind of data. So to tackle this and to understand or to improve this, I was like in 2018, I started my PhD in University of Salzburg. So I was looking at that time there was more of computer vision, deep learning, machine learning was hype mostly in Europe. Everyone was talking about what is like how we can use machine learning in everything almost. Still now it's a hot topic. So basically the thing is, this is a very simple example. If we have a single object, which is in this case is a cat, if we can just classify if this is a cat or not, or like what I do is object detection and instance segmentation, which are completely automatically done. So what I try to use this information for landslides. So if we have landslides and in images, in satellite images, how we can automatically detect them using machine learning. That was my, I'm not going to explain everything because I don't have time, but maybe someday I can do also hands-on session to make explanations about what is machine learning, why machine learning all of a sudden, how we can really apply ourselves. But this is just a simple overview where we can use remote sensing images and we can use machine learning algorithms to make a landslide map. Basically, like if I explain you in simple terms, deep learning, it's a field of study that gives computers the ability to learn without being explicitly programmed. So that's a definition. It is a subfield of AI or artificial intelligence. But now there are many applications of it in medical science, in geoscience. It has been there for last 10-15 years. There have been many machine learning models, but deep learning is much more new, and we have been using this like in deep learning. The most important and how it is different from machine learning is that it does the feature learning and classification, everything by itself. We don't need to provide features. What feature means is like the lines in like, for this is an example of a face, like lines or the edges of the nose or face, like eyes. This is just one example. So these features you don't have to provide in deep learning. So the model itself learn. But in my case, I use it for landslides. So now I'm going to show you some of the examples of what we have done or I have done in landslide detection in past 5 years or so. This was one of the first papers that I worked with people who were mostly working on refugee camp mapping, or completely different than landslides. So I was the only one who was working on landslides in University of Salzburg at that time. So I went to them and I asked them, I have some data from Nepal because I did my master's from ITC with the Professor K. Swan Weston, and then I was in field for 2 months in Nepal. So I gathered a lot of data. I collected data from Nepal. This was these are some of the images from Gorkha earthquake, which happened in 2015. So I went there physically. I collected a lot of data from satellite images, yes, but also went there on field work for 2 months. Then what we did is like try to map these landslides. Okay, manually, if we try to map each one of them, it takes a lot of time and effort. So my idea was how we can use these machine learning or deep learning algorithms to map these landslides automatically. So this is an example of red polygon is manual, and these are the blue ones are CNNs, which are convolution neural networks, deep learning algorithm derived or fully automatically derived polygons. We at that time we had many problems, like these villages were also landslides because they had similar spectral signatures to landslides. If we talk about in terms of the image bands and the spectral signatures. But then we remove these errors by using topographical features like digital elevation model or slope. These features, we just provided the features, but we did not tell the model that this you have to take into considerations these features, which is the benefit of using deep learning. Then I did this work where I changed from satellite image because that was 5-meter resolution. This one is 20 centimeter. Two different areas, UAV data in Uttarakhand. This one is more. This one is on from Rishikesh towards Kedarnath highway. I used a drone. It was published also in 2019. And then this one is on the other side of the highway towards Badrinath. So I fly the drone in two different areas, try to use these algorithms, try to understand if I train in one area and test in completely different area, which is different. Also the landslides were different. Then we were able to differentiate and map landslides. So for me, it was more about understanding how we can improve these landslide predictions. So we just, in this case, we just use one more layer, which is slope apart from RGB. And we remove the false positives in river beds, also false positive along the road. This was example of agriculture field. So we were able to remove this false positive just by using one single slope layer, which is very good information for the model to understand the elevation. If something is flat, it thinks that it is not a landslide. But this stage was still a learning process for me, and to understand how we can improve these further. Then what we did is in this case is another example where we tried to assess different optical data and topographical data individually. So these are some of the experiments that I did over time. So these are mostly related to my curiosity about how these models work, how these data work, and then mostly about modeling models and the data, the input data. Then there was this event in India where in 2018 Kerala floods and landslides. So everyone was focusing on floods. I decided to focus on landslides. So I did this work where I downloaded some of the planet images for Kodagu. It's a district in Karnataka, and the main city is called Madikari, I think, was affected a lot. As you see that the rainfall was a lot, and then because of the rainfall, the landslides were triggered. So I tried to map all of these landslides fully automatically by using these deep learning models, and just use a slope layer and just additional NDVI just to understand if we can do it in different area, because till now I was just using it in Himalayas. I was not sure if this kind of model can work in different area and also in different trigger, because these are mostly debris flows. And then it worked very well. And then all of these papers are published, and they all are open access. So if anyone is interested, you can just download them. They are for free. Also, the data for most of them are available on GitHub or on Genodo. This is another example of how we can map landslides, mostly from images from cam photo, like from images which are available on internet. This is also an automatic classification of non-nadir images. These are not satellite images. Everything which is available on internet, if we can identify landslides from them, this was just one approach. Then there was this paper where what we did was most of the time when landslides occur after rainfall, the images are cloudy. So to tackle that, we use SAR data. So we use SAR data to map landslide. This is an example of Hokkaido. We were able to map landslides quite accurately, even segmenting them. So this was just another approach where, okay, if we have clouds, what we do now? So this was just an answer to that. We have published some of these papers already, and one of them is as a review, I think is still related to this. But my main thing was like main contribution till now, you can say, is like I was trying to understand if we map landslides in Kodagu, for example, and try to test them in Japan, which is like completely different country, different Kodagu is rainfall induced, and Japan in Hokkaido was earthquake induced. Landslides, very different pattern. So what from this I just tried this, and then I came up with a bigger idea where I made this global landslide database for machine learning and deep learning training. What we did in this case is like we took some inventories which were available, try to refine them, and then download the planet images, which is like 3-meter resolution. And we use 5 rainfall induced and 5 earthquake induced events. And then we trained a model, we called it high resolution global landslide detection database. And this is freely available for anyone. The data set is freely available, the codes are available, and also the paper is freely available. So if anyone is interested, they can just go to this paper and try to use it for their own use case. Usually what I do is I teach how we can train this. No, like training, I can show training a deep learning model, but also I sometimes show how we test in a new area or if a new event happens. So this was mostly in 10 different areas. And then what we did next was to try to test it in completely different area where we don't know anything about landslide. The model don't know anything. So we just provide an image. Now the model should give us the landslide directly. I don't want to map landslides. I don't want to do anything. I just give a satellite image to the model and it should give me the inventories in polygon. So this is an example of Indonesia. This is another example of Haiti earthquake. In this, if you see, there are many false positives and many errors, but still it can be useful for rapid assessment. Like if something happens, if we provide such a map, which is a likelihood of like somewhat similar to the real situation, it can be very useful for the fast responders. So that was my goal at that time. And we also try to test this in many different areas. This one is an example of Brazil. One event happened. I tried, okay, let's see if our model works there. And these were the results. I didn't map them manually. They're all fully automated. And it just took me like 1 minute to do this. If I do it by hand, maybe it takes like maybe 20 minutes, 30 minutes. I don't know. It depends upon how fast you can click. And then this is an example. Everyone asked me, okay, how it is different from SAM, which is like from Facebook, the Meta, they have this model called SAM, segment anything model. These are the results of segment anything model, and a model which is trained. This is mostly I talk about the data set which is trained on landslides, because segment anything model, if we use for landslides, it gives you results like this. So thank you so much for listening to me. If you have any questions, I'm happy to answer. This is our team, or you can say there are some students also. So we have a team, it's called Machine Intelligence and Slope Stability Laboratory. We are in University of Padua, which is a very old university. It has completed 800 years last year. It is one of the most reputed universities in Europe. And I'm here for more than 3 years now. If anyone have any queries or want to learn these things, you can ask me or send me. If you just type my name, is the only name in the world, Sansar Rashmina. There is no other person on this name, so you can search me on Google. It's very easy to find. Thank you so much.
Thank you, Dr. Sansar. It was a great insight of mingling, or what should I say, merging of AI, ML, deep learning with geospatial technology, bringing an insight how landslide can be, especially the inventory part is very interesting, and creating a database globally it's a huge task. I can understand. I remember starting my career with a landslide information system way back, in 97, and I was given a pile of registers, with all the landslide inventory to be created that time. So yes, today with seeing the technology coming up and integrating these technologies with geospatial has definitely made a way out, bringing the data right in front of us at our tables, right at our desktops, from wherever you are in the globe. So thank you so very much. Now, the floor is open for questions. I would invite any audience who would like to ask any questions. Please raise your hands and you can unmute yourself, and we can and you can put up your questions, please. Do we have any questions?
Hello, am I audible?
Yes, please.
Hi, I'm Ashwati. I'm from Triple IT Bangalore. So I have one question. So I'm trying to work on like how we can create a susceptibility map for multi-hazards. So usually when landslide occurs, there's a chance of flood in the nearby areas as well. So how we can do the multi-hazard susceptibility mapping?
Anybody from our speakers would like to address this question, please? Any of our speakers? Dr. Himlata?
It's not a problem. If it's related to, you mean susceptibility of multi-hazard, but what multi-hazard? Because mostly if you look at Indian scenario, what we have is floods or landslides or land subsidence maybe, or maybe cyclone if you are more closer to the coast. So it always depends. There are many multi-hazard approaches which are published, but they are mostly weighted. Like you should put some weights on in the factors. But now I use, my perspective is different. I have used, if you look at my papers, I have used traditional methods like AHP, analytical hierarchy process, where you ask experts that this factor is important, then other factor, how much value will you give, 1 out of 9. And then also you can use data-driven models. So these are different approaches. You can use expert-based, knowledge-driven, data-driven. Now data-driven have many things. Now you can use statistical models, or you can now use AI models, but it's completely depends upon what you want to do. What is the use of that? Because as I said, susceptibility and hazard, they are different component, and try not to mix them because they give a very it gives, sometimes it undermines the main problem, because if you give a susceptibility map and then ask a community to go somewhere else and live somewhere else, it can have a big implication. So if you want to really address any particular issue or a research question, then you can think of, because if you look at the literature or there are many, I can only recall multi-hazard works from Professor K. Swan Weston. You can look at his papers. He mostly used these statistical weightings mostly for multi-hazard. But nowadays, I would suggest you can also try maybe machine learning algorithm. There are many available already. But if you have any particular question, I can answer. It was just a general overview of what can be done.
Thank you for the answer. So, I'm trying by trying using the machine learning models. So, for multi-hazard susceptibility mapping, I'm expecting a multi-output regression model. So, according to you, like how like in some of the papers which I have referred, there is a what you can say late fusion of the multiple hazards. So you will do flood susceptibility mapping separately, landslide susceptibility mapping separately, and you're fusing the maps together. But from my understanding, there the correlation of factors is not considered, or the correlation of multiple hazards is not considered. So can we do an early fusion approach by considering the correlation of factors, or like which modeling or which methodology would be better from the machine learning point of view to get a multi-output regression?
No, but like in this case, if you look at the interplay between conditioning factors should be addressed before, because this is what gives you an output which will be more robust instead of just utilizing or combining them or overlaying them afterwards. In this case, there are many machine learning models, mostly by Chinese authors. If you look at their approaches, their approach, sometimes they don't show in the paper what they really did. It's very unclear, but you can use some of the algorithms. What we use here in Padua is you can try to use XGBoost, but then try to see what novelty you can add to the modeling approach. But I would just say try to see the interplay between these factors and try to consider one thing called partial dependency plots. Try to understand how these susceptibility results, what is the impact of these factors on overall on the susceptibility. Try to see the impact of these conditioning factors on the overall model results. So this way you can use nowadays is called explainable AI. It's sharp values. Try to understand what is the importance of factors. Then you build on the next step. Then you think what can be what should I do, because sometimes the data is very critical. Sometimes one conditioning factors is getting a lot of attention than everything else. So there are many approaches. I cannot give you a single answer which machine learning algorithm, but you have to try to do experiments, try to understand which factor is contributing a lot, and out of that conditioning factor, which class of that factor is taking a lot of attention. But this is a very technical answer, but maybe if you want, I can explain later on.
Yes, I'll connect with you post the sessions. Thank you.
I have a question to Dr. S. Sri Krishnan. Yeah, thank you so
Yes,
much,
ma'am.
Ms. Krishnan. Your talk was very nice and informative, and it is based on the early warning system and the evacuation. So, my question is, can we work for early warning system, but we should work in such a way that maybe some technology or may something that we can mitigate those landslide As we know, their land is sliding. So can we protect those lands?
Ma'am, the question is twofold. Thank you for your comment also. So, means protection against these large scale landslides is practically not possible and also not economically feasible. But as also Professor Sansar has mentioned, if we identify the susceptible areas for landslides with high amount of precision, then those areas can be suggested for structural mitigation, what
Yeah.
the geotechnical engineers do. But we do have landslides at like scales of 6,000, 4,000 in numbers. Not all those landslides can be prevented before it happens. That's why we do have the non-structural mitigation measures. Because the landslides are so much in number, structural mitigation is not always feasible. But it should be there if we precisely identify those hotspots of landslides, and then the threat is also the risk and also the vulnerability. It's actually proven from those landslides. There, it has been done. Also in Uttarakhand, the sites of THDC, they have done very good landslide preventative measures compared to like other places where you do not have that much risk. If I answered your question.
Yeah, thank you so much for this. But another question is, there are so many sensors which has been put across the Uttarakhand by the government. So based on the data of those sensors, can we prioritize and we can make the
Yes,
mitigation
like
measures
there are
as possible
sensors
measures?
for weather forecasting, and but there are no implementation of sensors for like slope monitoring in a larger scale.
Yeah,
There are like few sites where like slope scale monitoring is being practiced, not only in Uttarakhand, also in like other states such as Himachal. IIT Mandi has installed like more than 30 sensors for one district where the real-time early warning system is being done. So, but in Uttarakhand, we do not have such dense network of sensors, especially for landslide early warning. But if we can extrapolate the other sensors, such as the seismological sensors, then can it be used for landslides? So those are still under like research option. They're
yeah.
still working on it.
Thank you so much. And my another question goes to Parvati ma'am. So yeah, it's really again a very interesting for me that you have elaborate the research on and the difficulties whatever you are facing during your construction of road network. So my question is ki you also they incorporated one parameter, that parameter is the heavy rain, high intensity rain. And if you see nowadays, there the rains are always high intensity. If you look at the Delhi, I'm belonging to Delhi. In Delhi, there is high intensity rain. The rain is the same amount, but it's a high intensity, and it is again increasing the landslide vulnerability. And I think it is because of the changing climate pattern, and it will be continuous in the coming years. So my question is, can we incorporate these data for some? Uh, can we create something mitigation measures to keep these things in mind?
Yes, ma'am. Actually, in most of the cases, when we design for a road infrastructure, we follow particular codal provisions. So in that codal provisions, even if it is flood or landslide, we follow the past rainfall data and past flood data. So highest one. So and we always take a little bit factor of safety to a margin and then design. This is what we do. However, in many cases, the problem is that everything is in hurry. Design is in hurry. In India, because everywhere we need it within 1 month. The DPR consultant doesn't have time, client doesn't have time, and the minister will be like committing a particular timeline. So time is very limited. So a elaborate study of the large area is not possible for this kind of with the that prediction of how much climate change is affecting this one, and how it should be incorporated in the design aspect and all, that is not there as of right now in any IRC guidelines or BIS guidelines. So what as a designer we can only be like take a extra factor of safety when we are considering the drainage measures or the design aspect. But when we consider a local area, like which I showed in the two case studies, there we can do elaborate analysis with the prediction and all the future susceptibility things. But for larger area, as I told you, for when we are designing now, I'm designing a northeast road stretch involved in around 150-kilometer stretch. So that is not possible for each, and because there will be hundreds of cross sections. So as of now, guidelines is not there. So obviously, the future research and study needs to be incorporated when all these predictions, from the geophysicist and geotechnical, everything has to be combined, and a good guideline needs to be implemented for the design.
I feel that I always, there is one suggestion I think just I wanted to give the director of DRRF, that normally it's my personal feeling that all the landslide happen in the hilly area, and that is again the tourist place. And the people, they are nowadays, they are very fond of to go on these tourist place, and somehow they never maintain, they just throw the plastics and all those things. And I think that is also contributing the climate and the affecting this
Environmental challenge.
environment and ecology. So I think we have to make some policy line or some guideline to based on the tourist people.
Yeah. I think we should have something like a round table and discuss this matter.
And
which
we
is-
need to submit those things to NDMA.
Yeah. I think we can think about that, and for future we can just work on those lines. I have a question from one of the audience here, from Nepal. He is asking that any of the speakers, are they conducting any research on avalanches flow, especially in the areas where glacier lakes that cause the outburst, causing flood and damage for the human settlement across the Himalayas. And any early warning systems have been developed in such cases. He says in Nepal, they had 2 glacier lakes outburst, especially in the Mount Everest region. And he's asking, do you think it might be an indication of precipitation or temperature increasing in Himalayan region? So any of the speaker would like to answer this question for him? Yeah, Dr. Himlata.
So I'm not working on glaciers, but one of my team members is working. Maybe I can send out her contact, and we can contact her, and she's doing an excellent result on Himalayan glaciers.
Okay, great. I would request if anybody has a specific questions or something, they can just send us an email on info@drf.org.in, and we can pass it on to the our speakers. And I have a question for you, Dr. Hemlata. You had mentioned about landslide tracker app, Landslide, right? So a landslip, yeah, sorry. I just wanted to know what is this just applicable in the area of research you have done this, or it could be applicable across India?
It's freely available in Play Store, and both Android and iOS versions are available. And this app is developed as part of Landslide project. And Landslide project was a British NERC funding from the UK, and 9 partners around the globe were involved in that. And from India, Amrita and GSI were involved, and Amrita developed this app further. And this app, in this app, it is basically used, it can be used by anyone. And we designed this app so that community members, researchers, academicians, students, anybody can use the app. And they can, if they have a landslide, especially we have trained our community people for doing this. When they find a landslide, they record the landslide in the landslide tracker app. So they take, they enter what is the location, lat long. If everyone has a smartphone, and it's easy for them to get the lat long. It's a lat long, and what's the type of a landslide, and at different levels also. So if you are a general public, the number of questions you get is simple, like what's the location? Can you upload a map, and on which road or which highway is there any landmark? Also, so very simple questions that a layman can understand. And if it is a researcher or if it is a geologist, the level of questions get deep more, like what is the type of slide? Is it a debris flow? Is it a slip, or is it a it gets into the detail, and also it gets into some more details, like if it is a geologist, what is the type of rock, what is the material, such things. So this is like in the area we have the deployments, our community people use that, and it's really useful for us, because when a landslide happens, some of our community members do this, and we have trained few people to do this work also. So for a single landslide, we get like 10 or 15 entries, and then we know who are the trained members, and we take them, and we are also trying to develop,
No, my question was, what is it covering the entire Indian geographical borders?
Yes.
Even that is one thing. So then it should be promoted in all those areas, specifically the entire Himalayan belt, where we actually face this kind of tragedies, and especially with the Western Ghats as well. So I think it should be promoted. If such an informative app is there, and which can actually help the community and the authorities to take care. So
yeah, you can try. The name of the app is Landslide Tracker app. Not only for India, it can we have entries from other countries also.
Okay. Thank you so much.
Thank you.
So, do we have any other questions from our audience? There are certain questions which is outside landslide. You can just put those questions to our email, which I've just shared, info@drrf.org.in, and we can forward to the relevant speaker accordingly. Is there any other questions from our audience? You can raise your hands, and you can unmute yourself, and you can ask. I think we don't have any other questions right now. So I'll take this opportunity to thank all our speakers for taking out their time from this busy schedule, especially it's a weekend. I know it's a personal time, but yes, thank you so very much for taking out time and coming onto this forum at a very short notice. That was very, I really appreciate that to all our speakers for this. So, and those who have missed out this full session, it will be available on our YouTube channel soon, and we'll circulate those links soon on the social media as well. So I would take this opportunity to thank everyone, Dr. Sri Krishnan, Dr. Parvati, Dr. Himlata, Dr. Sansar, for giving us this, coming and presenting the need of the hour, and really the requirement, how we are progressing, especially in this sector at this moment. So thank you so very much. Thank you very much.
Thank you, madam. Thank you.